Good morning, all of you. Thank you for attending today's class. Uh, Let me go through what we discussed in the last class and what we are planning to do in this today's lecture. Okay. So what we had covered so far was we started off with indefinite integral and stated some rules of integration. Then we discussed some applications, getting the total curve from the marginal function, uh, getting flows from stocks. And then we moved on to Riemann integral, which is part of the discussion on definite integrals. So in this class, we are going to show that the Riemann sum can be obtained in a slightly different way. We'll proceed to the fundamental theorem of integral calculus, and well, we'll look at some applications. Okay. Now, as we had discussed in the last class, we can think of a sum S as an approximation of the area under curve over a given interval. So we have a function which gives this green curve or line, and we want to find out the area under this function from 0 to this point. So we can divide this up into different uh, so to repeat that, we have the function which generates this green line, and we want to find the area under this curve or line from 2 points. The interval is 0 to this point. So we divide this into certain sub-intervals. Here we have divided the interval into 4 sub-intervals. We take any point omega in each sub-interval, and we simply draw a box. The height of the box is the omega up till this function, and the base is the sub interval. So we take different omegas and we draw different boxes, and if we sum them up, we get the Riemann integral. So the Riemann sum is an approximation of the area under a curve over a given interval. Now, as we have pointed out, it doesn't seem to be a very uh, pleasing idea because of two reasons. First of all, the subintervals that we use are arbitrarily drawn. And secondly, the point omega that we are taking within each interval, that also is chosen in an arbitrary fashion. So because of these two arbitrary components, we have shown that the Riemann sum can vary from person to person, depending on what the omega is, what the partitions are. So therefore, what we have is that the area or Riemann sum depends on our choices of subintervals, our choices of uh, omegas, and it is not well defined. Okay, let's see. Okay, so we had pointed out in the last class that what we can do is we can reduce the length of the subinterval. We can make the subintervals finer and finer such that the length of the widest subinterval approaches 0. In that case, a convergence sequence of values for S will be generated, and the limit of such a sequence is the area under the curve. Now we can approach this problem in a slightly different way. We consider two extreme ways of choosing the point omega within each sub-interval. First, we can choose omega to generate the smallest possible value for the Riemann sum S. Let's show this using a diagram. Okay. Okay. So uh, let's start from here. Okay. So we have, let us see, this is the interval, and we divide this up into certain sub intervals. Okay. So let us see if we are taking we want to find out the Riemann sum for the closed interval 0a, and we have some other sub intervals over here which we are not drawing. Okay. Now we can take the Riemann sum. Let's use a different diagram. We can take the Riemann sum over here. Now, if we, for a particular sub interval, we took omega 1, f of omega 1 into, right, these were the, and so on. And so let us suppose that the sub intervals are given and the problem is how to choose omega. So what is the minimum value of omega?
Zero.
Sir,
Yeah,
0.
So
yeah.
zero.
So yeah, in fact, if we think of the boundaries as XL or XH, or we can think it of XI, XI minus 1, the minimum values will be over here. Okay. If we take the second subinterval, the minimum value will be here, and all these 4 points. Okay, so here there's no omega. Let us take F1 over here. So we can define F omega like this. Okay, now just remove this. Now, instead of taking omega as the minimum, if we just shift omega to a point like this, Okay, so we started off with omega xi minus 1, which is equal to, let us say, xl. Okay, then we take xl plus a small value. Okay, so what happens to the functional value? This is higher. Okay, this was 0. Here it is this much. If you increase it even more, we make it over here, we can see that the functional value is going up. Okay, and how far can we go for the first subinterval? We can go only up to this amount. Okay, so that means this is the maximum that we can go up to. Beyond this, we are crossing the, we are going beyond the sub interval. So that means the minimum value, the minimum, the lowest value of omega possible is x I minus 1. This will generate the smallest sum. I call this SL or S min. And what is the S max? It will be xi. Okay, so that means if we take the, if we want to find out the smallest sum of the Riemann integral, we should take these values. First is over here, then is over here. Next we move to here, here, and so on. Okay, but if you want to take the maximum values, then sorry, just give me a moment. If you want to take the maximum values, then we should take it at starting from x1 like this. Okay, so if you want to take the maximum ones, we should take the upper point of the boundary. So that means S min will be, and S max will be, okay. So this will give omega, we are using omega min and we are using omega max. Okay. Or if you want to use a, sorry, there's a notation change. I want to just have a look at it. Yeah. So we use a slightly different notation over here. We are going to use a notation. S min will be, okay. So this is underscore and x max will be like this. Okay, so underscore means that we have taken the minimum values. Um, if it is at the top, then we have taken the maximum values. Any questions so far? Okay. So that means we can find out the Riemann sum in different ways, but the minimum value, the minimum value of the Riemann sum will be generated if we choose omega equal to the lowest point in the subinterval xi minus 1. And if you want to take the maximum point, we will get the, we have to choose the omega such that it is equal to xi, the maximum point, the upper point of each subinterval. So S mean the Riemann sum is function of omega Li. As we know that this is, we are going to write this as omega underscore. And this is the maximum, and we are going to use a slightly different notation. In each case, we are taking this del I is the same, but what is happening is the value of omega is changing. So the functional value will also change. Okay. Okay, so this is what we have shown, that as we are increasing the value of omega within a subinterval, the height is going up. The length is the same, the height is going up, so that the Riemann sum is going to increase. And the minimum is this lower boundary, the maximum is the upper boundary. Okay, so here we have found out the Riemann sum in two extreme ways. This is S mean and this is S max. So over here, we start from 0. The function is fx equal to 2x. So the first rectangle is has an area equal to 0. This is the second rectangle, A2, A3, A4. This is the last one. Here, when we are finding out the maximum Riemann sum, we have four rectangles, B1, B2, B3, B4. So for the first subinterval, the rectangles are A1, which is 0, and B1, which is max. For the second subinterval, we have A2 and B2. As you can see, these represent two extremes. So if we sum them up, we are going to get S mean, which is 0.75, and S max equal to 1.25. So if you take these same intervals, 0.25, zero point 0.5, 0.75, whatever the value of omega you take will lie between, will generate a Riemann sum which is between 0.75 and 1.25. Okay, this is obvious. Okay. Now it is clear, it should be clear that S mean is always an underestimate of the area under the curve. Why is it an underestimate? We have dropped out this part. We have dropped out this part, this part. These white parts are being dropped. Okay, so this is being excluded. On the other hand, we are including this rectangle, this triangle, sorry. So we are taking something extra. In the first case, we dropped something, we dropped these portions, and in the second part, we have included some triangles. Okay, so basically that means that we are underestimating the area under the curve, and in this case, we are overestimating the area under the curve. Now, as we said, that a solution is that if we can use finer and finer partitions. So that means what we are doing is we are shifting this line. Okay, so I'll just draw this. So this is 1 and 0. So instead of taking 0.25, okay, so the first subinterval was 0.25. Okay, we reduced the length 0.24, 0.23. So what will happen to S max minus S min? Here it is 0.50. But if we take instead of 0.25, if we make the interval, bring the interval over here, what will happen to the Riemann sum? The difference between S max and S min, it is going to deteriorate. And as we are going to shift this interval leftwards, the difference between S max and S min is going to go down. So as the sub intervals become progressively smaller, S max is going to approach S min. Okay. And in the extreme case, the limiting case, we are going to have a situation when S max tends to S min. Okay, so this interval is going to shift. And what is the limiting case? It becomes this. So as I've told you, in that case, instead of rectangles, we are going to have vertical lines. Okay. So as we are progressively reducing the length of the subinterval, S min and S max should converge to the same value. Okay. Since omega min, sorry, omega max is converging to omega min, S min will also converge to S max and give the same Riemann sum.
Sir, is it
Yes.
so S max converging to S min or S min converging to S max?
Yeah, sorry. We have a tendency to write min first. That's why I wrote it. Oh, yeah. Okay. Thank you for pointing it out. So let's look at it formally. So here we have used the underscore. This means we are generating the minimum Riemann sum. So S min is simply summation of these are the subintervals into functional value at each omega. So here we have taken the minimum value of omega, omega underscore. Okay. So omega underscore is basically xi minus 1. If your interval is xi minus 1, xi, this is omega underscore. And this will be omega over score. right? Okay. Now our functional value was 2x. So if we take xi minus 1, sorry, it will be simply I minus 1, 2 into I minus 1 by n. And the subinterval, length of the subinterval is 1 by n. So as you can see in the first case, I minus 1 is how much? This is the first subinterval. So 1 minus 1 by n. The second subinterval, it will be 2 minus 1 by n. Then 3 minus 1. So it's going to go up like 0 by n, 1 by n, 2 by n until we reach the last subinterval. In that case, it will be n minus 1 by n. Okay. Okay. Now just forget about I minus 1. 2 comes out and n square, that also we can bring out. So we simply have 2 by n square summation of I minus 1. And I minus 1 is 0 plus 1 plus 2 plus 3 up till n minus 1. So the summation is given by n by 2 into n minus 1. So we substitute this over here and we get this expression. You can check this easily if you just um, cancel out the n's. You're going to get this term. Okay. So the value of S mean is equal to 1 minus 1 by n. Is it clear? Or do you want me to repeat some point? Okay,
Sir, could you show the previous slide once?
just once.
Yes, sir, I'm copying the last line. Yes, sir, thank you so much.
Yeah. By the way, these values should have been 0 by 1, 1 by n. I couldn't write this properly. Okay. Now let's go to the other extreme, S max. In case of S max, see this is the boundary subinterval. So we have to take xi for each omega. So for the partitions, xi will be 1 by n. Okay, so S max is equal to summation of function of omega I, but this is overscore, so omega max into del I. The del I, as we have shown, is 1 by n. Okay. Now omega, we substitute this xi in place of omega, right? And xi is given by I by n. In the previous case, it was I minus 1 by n. Here it is in. Okay. So again, we can take out the 2 and the n squares, and we simply have summation I, which is 1, 2, 3, so on, up till n. Okay, so it goes like this. 1, 2, 3, up till n. We are taking this point, but we are not taking this point. Okay, so the summation of this is simply n plus 1 by 2 into n. So we substitute this over here, and after some algebraic manipulation, we get 1 plus 1 by n. Okay, so in the earlier case, it was this was S mean, and this is S max. Okay, I'll wait for you to write it down, then I'll go to the next slide.
So copied. It's okay.
Okay, so our remember that our objective is to show that in the limiting case, S min is equal to S max. And we've shown that we don't have this. I mean, S min is plus 1 by n, sorry, S min is minus 1 by n, and S max is plus 1 by n. Okay, so very clearly, S min is less than S max, right? Because in this case, we are subtracting something from 1. Here, we are adding something to 1. Okay, now, so S max is greater than S min, but as the partition becomes arbitrarily fine, how can we make the partition arbitrarily fine? See, this is the main subinterval. I have n is 2 over here. I've got two subintervals. Now suppose I take n equal to 4. Okay. So I start bringing this closer. So if I bring this closer, that means I've got to increase the number of subintervals. N will go up, increase. And what is the maximum value of n? N tends to plus infinity. So in that case, we have S min, and this is right. So both of them become 0. So we simply have S min, right? So in the limiting case, limit S max n tends to infinity is equal to limit of n tends to infinity S min, and the value is 1. So we see that if the function is integrable and the limit is the area under the curve. Okay. So we have shown that the Riemann sum apparently is arbitrary and can give, well, overestimates, underestimates. But if we take the limiting case when the number of subintervals tends to infinity, in that case, the Riemann sum will give an almost accurate measure under the curve. There will be a difference, but it's going to be, it will tend to 0. Okay, is it clear?
Sir, I have a question.
Yes,
Uh,
please.
Sir, in the minimum case, while we are increasing n, how can we be sure that it means that the first minimum n value is being shifted to the left? It can be like the first minimum n value is at the same place and we're increasing other numbers to the right.
Sorry, I didn't get your point. Okay, let's look at this graph. So these
Yes.
are the initial subintervals. Okay, so you're saying that we are shifting
Yes,
this.
sir. We are increasing, we are making the partitions even finer. So we are
Yeah.
increasing the number of n's. So how can we be sure that 1 by n is being shifted to the left? It can also happen that we are just increasing number of partitions to the right of the minimum partition.
Oh, we assume that the subintervals are of equal length.
Okay, okay. Okay, sir. Thank you.
Yeah. In that case, you will have to squeeze. Yeah. What you're basically saying is, I keep this constant, and over
Yes,
here,
sir.
I'm increasing the subintervals.
Yes, sir.
No, it's a uniform case. Okay. So we see that a function is integrable on the closed interval AB if for every epsilon which is positive, there is some delta which is also positive, such that this Riemann sum minus L is the Riemann sum, the absolute value of this will be less than epsilon. Okay. So for any partition AB, and the maximum del I possible is less than del. The maximum subinterval possible is less than del. Okay, so we call this value the definite integral of fx over the interval ab and write this as integral a to b fx dx is equal to L. So what it implies is that if we increase, okay, so two things are important over here. This is the definition, the technical definition, and this is these two areas are the interpretation. So this is the formula, and here is the interpretation. So if a function is integrable on an interval, closed interval AB, right? So if we take finer and finer partitions, if we break up this partition into an infinite number of equal subintervals and take the omega, the Riemann sum must converge to some value L. In the example that we discussed, what was the value of L? Or 3? What is the value of L in in the example that we took? Prithviraj?
Sir, 1.
It should be.
It should be 1. See, what are we doing over here? Joto, what is the maximum value? 1 plus 1 by n. আর এখানে minimum value হচ্ছে 1 by 1 minus 1 by n. Okay, so the Riemann sum, depending on the number of intervals and omega, the Riemann sum is going to vary between these two values. এটা তো আগেই আমরা বলেছিলাম. The Riemann sum is going to vary between 0.75 to 1.25. As we are gradually shifting it, making the subintervals smaller and smaller, the limiting case will be this. The two will converge. And this is the value of L. Okay? So at this limiting value, it doesn't matter which omega we choose within the subinterval. Whether we go for the smallest omega or the maximum omega, or we go for an intermediate value of omega, in all cases, they will converge to the same value. So this method of finding the area under curve is somewhat tedious, but if the function is continuous, then we can apply the fundamental theorem of integral calculus. So basically the Riemann sum argues that you have to divide it up into an infinite number of subintervals. Take sums. And I mean, see, if you do this like this, you take sums, you add them up like this, it's going to be tedious. It's going to be a very pretty long process. But the advantage is now we can apply the fundamental theorem of integral calculus. If the function is continuous on the closed interval AB, and if capital Fx is the indefinite integral of small fx, we can write integral of a to b small fx dx equal to capital Fb minus Fa, capital Fa. Okay, so here we are taking fx being. If you go back, see this term is this term. So the Riemann sum can be simply found out by taking we find out capital F, we evaluate it at A, we evaluate it at B, and we take the difference. So instead of taking a series of sums, we just have to find out the integral at 2 points and take the difference. Okay, so just check these values over here. Please do it yourself. Remember that I can ask you to do the sums in the Viva. So do practice. I mean, I'm not going through all the practice exercises, but unless you go through it, you're going to end up in problem. Okay, here it's a bit difficult, so I've just given you the integral. I've given you capital Fx. Okay, I'm moving to the next slide.
Yes, sir.
So we are going to the economic applications. So um, now we have said that in integral calculus, one of the applications of integral calculus is uh, when we find out the flow from a stock. Now suppose capital KT is a stock of capital at a particular time t. What is the corresponding flow concept? It is investment, changes in the capital stock. IT is the rate of net investment, gross investment less depreciation. Sorry, just a minute, one second. Okay, so we have capital and IT is the investment. Okay, now we want to find out what is the investment. Okay, so investment is the difference between the capital stock in the two periods. Investment is the increase in capital stock, right? So KT plus del T. Time has gone up. So this is the initial capital stock and this is the current capital stock. And the difference gives the addition to the capital stock in this period, T plus del T. And if you find out the average rate at which capital stock changes, we have to divide this by del T. Okay. So that means if we are finding out the capital stock, the change in capital stock between two periods, let us say today is year one and we want to find it out after 5 years, then we simply take K1 and we take K6 and what do we divide this by?
Time period.
Yeah, so what is the time period? What is del T over here?
B minus A.
So B minus 1.
Where are you getting B? Simply give
This,
the, I'm not looking into this diagram. Just look at this and tell me
this is, so that
what
is
is
6.
del T.
B
So that is
minus
6 minus 1.
or 6 minus 1, yeah. 5.
Yeah, so this is 5. Okay, okay, okay. So by definition, if del T tends to infinity, then dk, this is equal to dk by dt, the change in capital over change in time is equal to dk by dt, and this is investment. Okay, okay. So we want to find out how much investment has occurred between two periods, A and B. So we start at A, we have a certain capital stock, and the capital stock increases when we reach this point. Okay, so this is simply the Riemann sum, right? And to find this out, sorry, there's an extra integral over here. This should not be. This is it dt. We integrate this, or we simply take the Riemann sum. Okay, so this is the investment function. We simply take the Riemann sum, and as we've got it from here, the investment is this minus this. Okay,
So could you show the previous line once?
yeah.
Thank you, sir.
Okay. So over here, we take the discrete case. So there's a firm, T is 1. It has a initial stock of capital given by 10 million. So we can write K1 equal to 10 million. We assume that capital does not depreciate and the firm invests in new capital at a rate of 1.5 million per year. And this goes on for 3 years. So what is the investment? It is 1.5 for t equal to 1, 2, and 3. What is the capital stock at the end of the year? So it is 10 million. K3 is K1 plus you have investment in the 3 periods. So this is 10 million. And every year we have an investment of 1.5 million. So if we sum it up, we get 14.5 million. Okay. So what is the total investment? It is K3 minus K1, right? If we just take this over here, so K3 is 14.5, K1 is 10. So the total investment is this 4.5. So if I give you a discrete problem, you have to find it out basically using the Ryman sum. Okay, over here we take a continuous case. A firm starts with t equal to 0. Capital stock is 5 lakhs and the net investment is 600 t square over the next 10 years. So what is the planned or anticipated capital stock after 10 years. So K10 is equal to, sorry, this 9 should not be there. This is the initial capital stock plus the investment over 10 years. So integral of 0 to 10 IT dt. Now K0 is 5 lakh. We put this, and this is simply we put in the investment function. So we get 5 lakhs plus this is the integral, and you have to evaluate it from 0 to 10. Okay, so the planned capital level of capital stock after 10 years will be 7 lakhs. Okay. Okay. Next we come to the second theorem, and which is we are approaching the end of the lecture. If f is a continuous function on the closed interval AB, then for any x which lies within AB, the function, sorry, let me put this, belongs to AB, the function fx is defined by a to x ft dt, which is a indefinite integral of f. Okay. So over here, what we are basically trying to say is that we have a function like this. It's a closed interval, and we have a function like this. So the Riemann sum, the fundamental theorem tells us how to evaluate this. It will be right. Now the second theorem states that if we take any subinterval, see, remember that it's a continuous function in this range. We don't know what comes over here. It may be like this, it may be a step function, whatever. But within A to B, it is continuous. So if we take an interval like this, and we want to find out the area between A to X, we can again apply the fundamental theorem. It will be simply, uh, just to avoid confusion, let's call this X1. This will be simply AX1. Okay. If you want to find out the interval over here, area between these 2 points, again we can do so. This will be what? What will come in the subscript?
P and X2.
Yeah. And if we want to find out this area, this
X2
is
and X1.
X1 and X2.
okay. The important thing is the function is continuous in this range A to B. So if it is continuous in the range A to B, we can find, you apply the fundamental theorem to any sub interval within this range. If you want to apply it after, beyond B or before A, well, we don't know whether it is continuous or not. So we have a problem. But it is continuous between A and B, so we can apply the fundamental theorem. Okay. So again, I've given you some problems. So, well, I mean, if you can find, if you want to find out, it's your game. So we have completed a detailed discussion about the Riemann sum, and we have shown how to use definite integrals to find out capital stock investment. In the next lecture, we are going to address two issues: properties of integrals and the applications to consumer, finding out consumer and producer surplus. Have you done this? The Marshallian theory of surplus?
Yes, sir. Like the theory part, we covered it last semester.
Okay. Both consumer, I know you have covered consumer surplus. Do you know what is producer surplus?
Yes, sir.
Okay.
Yes.
Okay. So we'll discuss this in the next class. Okay. Okay. So in that case, I'll just very briefly, I'll repeat the classical optimization. In case of the classical optimization problem, we maximize a function subject to a constraint, or we take we minimize a function subject to a constraint. Now the important thing is that the function that we are maximizing or minimizing will be nonlinear. When we are coming to the constraints, this has two important properties. One is it is linear, and secondly, it is satisfied as an equality. Okay, so that means if we have, I mean, if we take the utility maximization case, then the solution value will be on the constraint, on the budget line. Okay, it is not an interior point. Okay, it will be a point, any point like this. So technically, you can consume less, you can save, right? So you don't spend your entire income, but you save part of it. But when you arrive at a solution, you will see that that there will be no savings. So you strictly have m equal to p1 x2 plus p2 x2. Okay. So to repeat, the objective function is nonlinear, the constraint is linear, and it is satisfies as an equality. Uh, we can generalize this and make this also nonlinear, but generally we work with linear problems. Now, primal is the original optimization problem. If it is a max, it can be converted to a equivalent minimization problem. This problem is called dual. On the other hand, if the original problem is minimizing something, then again we can convert this to an equivalent problem, which will be a maximization exercise. Okay, and this again is called the dual. So the primal is the original problem, and the optimization problem is the dual is the equivalent of this. And there's a theorem which states that the solution of the primal and dual is same. So whether we take the maximum or whether we take the equivalent minimum, we are going to get the same solution values. In case of utility maximization, suppose we get a solution set x1 star, x star 2, then we convert this to the dual, which is minimize expenditure subject to utility constraint. In that case, again, the solution will be identical x1 star, x star 2. So if it is f5 and 10, the dual will also have a solution of 5 and 10. Okay, so the important thing is that you have to note are these things. It is nonlinear and it is satisfied as an equality. In case of a linear programming,
So from here, do we get only sums?
I'll tell you. In case of linear programming, what happens is, again, I'll work with just maximization. See, this was the maximization problem. Okay, this is not obvious, so I'm going to write it down. The ops maximize what you're maximizing, the objective function, is linear. So this is what is new. And what is new over here? How did we write it in the classical case? So here it is not an equality constraint, it is an inequality constraint. Okay. In case of min, it will be okay. So the important thing is, firstly, it is linear, and secondly, the constraint is inequality. However, even though it is an inequality, generally you will see it will be satisfied at the boundary. So that means if you have a constraint like this, if generally you have a set of constraints, so at what point will you satisfy both the constraints? This.
Intersection,
Yeah.
yes, quadrilateral.
So this is the feasible point. So it can be shown that it will be at points like these. Depending on the nature of the objective function, the extremum points, the boundary points at the extreme, not any boundary point, not these for instance, but these points, these 3 points, 1, 2, 3. The solution will occur at one of these 3 points. In case of nonlinear programming, Well, it depends, right? I mean, if it is maximum, it should be, and if it is minimum, it should be. Okay. So first look at this part. Compare this part with classical optimization. Is it same or different?
In classical, we only had equality.
Yeah. So it is not like classical optimization where you had equality constraints. So it is similar to linear programming problems where you have inequality constraints, right? Now we come to this. This is nonlinear. So if we compare this with nonlinear programming and classical optimization, which one does it resemble?
Classical.
It is similar to classical. Linear programming was objective function was linear. So that means you can see it's a more complex version of an optimization exercise which combines the complexities of classical optimization. You have a nonlinear objective function and the complexities of a linear programming problem when you have inequality constraints. But again, even if you have, uh, okay, so over here we use something called Kuntaka conditions. So the normal course is, I mean, what I teach is that we discuss, we derive the Kuntaka conditions graphically, and then there are some applications. Like, I don't know whether you have SMS done it or not, that you have a revenue maximizing monopolist. So the revenue function is given, the monopolist maximizes this subject to a profit constraint. So what is the output level? So this is one. Secondly, you have the consumer problem. So maximize utility subject to budget constraint. But now you have rationing. So that means you have maybe you have food coupons which you have to purchase, and using those food coupons, you can go for you can buy the get hold of the commodities. So there are some two or three problems like this which I normally discuss. So discuss within yourself and let me know whether you're interested in NLP or not. So far as applications or use is concerned, I mean it's not very important that you finish Kuntaka or nonlinear programming at this stage. If you know the difference between the three problems, that is all. If you can do Kuntaka, obviously it's better because it's in your course and this is a nonlinear course. So if you can do nonlinear, it is even better. But I don't think it's really essential or it will really help you. Okay. So
Okay, sir.
Discuss with me yourself and just let me know. Okay. And